I will introduce the cumulative global constraint used for solving the cumulative scheduling problem. Similar to the all different constraints, the cumulative constraint can be decomposed into a set of simple constraints. Let me introduce the attribute of the cumulative activity. A rectangle is used to represent an activity. The length of the rectangle is the fixed duration of the activity. The height of the rectangle represents the resource requirement of the activity. When an activity starts, it cannot be interrupted until its completion time. An integer decision variable is associated to an activity. The range domain of the decision variable is from its early start time to its latest start time. We also introduce a view of the start variable plus the duration for representing the ending variable of an activity. Notice that the ending time is by definition the time just after the last resource consumption. A cumulative constraint receives as argument an array of start time variable, an array of fixed duration, an array of fixed resource requirement, and the capacity of the resource. Here is an example of 6 activity that does not violate the resource capacity, since at any time the sum of cumulative requirement never exceeds the capacity of the resource. The formal definition of the cumulative constraint is given by the formula 1. The interpretation of this formula is, at any time, the sum of the requirement of the activity overlapping the time cannot exceed the capacity C of the resource. The strict inequality below the sum comes from the fact that activity does not consume any more at the ending time. Before introducing the decomposition, let us recall what a refined constraint is. It is a constraint that is linked with a Boolean variable that represents the truth of the constraint. Consider the following example. In this example, B is true if and only if x is less or equal to y. With the given domain, we cannot prune anything. Let us remove the value 1 and 5 from the domain of y. Clearly, x cannot be smaller than y, and therefore, we remove the value truth in the domain of B. If B is set to true, x cannot be smaller than the value 0 of y, and therefore, we remove the value 0 from the domain of y. The decomposition consists in translating the definition of the constraint. First, we capture the fact that an activity I overlaps time t with a refined constraint. The Boolean variable OIT is true if the activity I overlaps time t. Second, we enforce the sum over all activity of cumulative requirement to be less or equal to the capacity of the resource. The following example illustrates the behavior of Boolean variable used during the reunification. When activity I starts early, it overlaps the interval from 6 to 7. When it starts later, it also overlaps the interval from 6 to 7. Therefore, the refined constraint will set the Boolean OI6 and OI7 to truth. The other Boolean variable remain unchanged. Let us illustrate the possible filtering of the decomposition on a small example of two activities. Each activity requires 1 unit of the resource, and the resource is of capacity 1. It means that the two activities cannot overlap. We previously see that the Boolean variable OI6 and OI7 are set to truth by the refined constraint because whatever the start of this activity is always overlap times 6 and 7. Since the capacity of the resource is 1, the sum constraint applied to times 6 will force the Boolean OG6 to become false at times 6. The same conclusion happened at times 7. It means that activity J cannot overlap times 6 and 7. We need to push the start time of activity J after times 7. With the new time window of activity J, new Boolean variables are set to truth. The sum constraint applied on time 8 to 11 force the activity I to end before time 8. The filtering of the decomposition is quite good, but due to the discretization of the time, we introduce a lot of variables and sum constraints. The fixed point computation can thus be quite slow and proportional to the horizon. For example, with 10 activity and an horizon of 10 hours with a graduation less than 1 minute, we need thousands of variables and sum constraints. Instead, we will prefer to limit the number of variables and make sure that the filtering only depends on the number of activity. In the next video, we will show how to perform the same filtering in order of n squared with the so-called timetable filtering.